Okay, so thank you very much to Professor Ogawa for inviting me to participate in this. And so this is my first time doing this with Zoom, and we'll see how this goes. But so this is a joint work I'm going to describe, originating with a former PhD student of mine, Jia Guo, who is at UC Riverside, and with a current student of mine, Sarafa Ayanyawura at UBC. Okay. So the philosophy of what we want to do today basically is to look at a model of a PDE-ODE model that can give rise to triggered oscillations, right? That is really due to a coupling of an autoinducer, the bulk diffusion in a 2D domain. So the picture is we think of signaling compartments, which are small, and so we can think of the concentrations as being well mixed, that are coupled spatially through a passive diffusion equation, okay, called the autoinducer in 2D. Okay, so the question you want to ask is, can you trigger oscillations in the small cells, right, that otherwise would not occur without the coupling? Okay, so in particular, there's a phenomena that's known as dynamic quorum sensing, whereby cellular concentrations begin to oscillate and synchronize their dynamics when their number, right, when the number of such cells exceeds a threshold. And so if you think of capital omega here as being the area of the domain, this is usually regulated by a cell density parameter, which I call here rho. Usually in the past, dynamic quorum sensing behavior has been studied in the so-called well-mixed limit, where you end up getting basically an ODE system with a global coupling through a mean field, right? But there's also a friend of dynamic quorum sensing, which is what I call here and what's known as diffusion sensing, which is a little bit more nebulous in the literature, but it's where cells oscillate and synchronize their dynamics based on spatial cues. In particular, the spatial configuration of the cells. If cells, which we think of as being disks, are more closely spaced, it might be easier to synchronize their activity. If the magnitude also of the diffusivity, D, of the extracellular chemical is larger, okay, then there's better communication between the cells. But to study this, you really need a PDE-based model. So can you combine these two things in one universal model that you can then investigate different phenomena? Okay, so in nature, quorum sensing and collective behavior in cells due to an autoinducer field, right, is a well-known concept. Okay, so in glycolysis, right, starving yeast cells undergo oscillations that's mediated by acetaldehyde, which is known to be the autoinducer. And this has been studied in the literature that there's a switch-like response. Social amoeba in the early stages of before they begin to exhibit aggregation, with cyclic AMP organizing the aggregation, that they start sending cues, right? Right? But on a macro scale, the same phenomena, much larger spatial scale, of course, is with this work of the Ken Showalter group, which has to do with catalyst bead particles, which are small spheres immersed in a chemical mixture. The spheres are coated with a chemically reactive coating, right? And these things can exhibit oscillatory behavior, right, once the cell density exceeds a threshold. So Ken Showalter in his group has been working on this. But there's another type of collective behavior that can occur, right? And this is the phenomena of bioluminescence, right? Originating from marine bacterium here, Vibrio fischeri, right? Whereby there's, and also similar phenomena, at least mathematically, right? In a human pathogen, right? Where the cell density does not lead to an oscillation, but leads to a sudden emergence of collective behavior, right? Everything is monotonic, but as you increase the cell density, there's a switch to a new large amplitude type solution. So here's the picture from the paper here at the bottom by Gregor's group, okay, in 2010 of cyclic AMP, right? So this is a bunch of social amoeba, okay, 180 cells, right? So before they start aggregating to form a fruiting body, this is the last stage. At the beginning, before they start forming a fruiting body, they exhibit some type of intracellular oscillation, some type of collective oscillations that triggers a signal that they should aggregate. So we're interested here at how do you actually, or where does this collective oscillation originate from? So the question here is the oscillation an intrinsic property of the cells? In other words, are they oscillating originally and then they collectively synchronize their activities? Or does it only occur at the population level via a switch? Okay, so as I mentioned, there's two types of quorum sensing systems. Switch-like emergence of intracellular oscillations as a density increases. Right? So this is under this kind of group setting, okay? But there's also the transitions between low amplitude and large amplitude bistable states as the cell density increases. And bioluminescence and this human pathogen is an example of that. What I'm going to do today is focus on the first idea here, is the emergence of intracellular oscillations, although the modeling framework we adopt applies equally well to the second case. You just have to change the reaction kinetics. So the key ingredient that is needed is an intracellular autocatalytic signal, some type of thing that can generate oscillations, right, if it's activated sufficiently in a strong way. But an extracellular communication mechanism, which is this bulk diffusion field or autoinducer, that influences or provides feedback to the autocatalytic growth. But the idea here is that the oscillations and ultimate synchronization occurs by a switch-like response to elevated levels of the autoinducer. It is the idea that there's going to be all of a sudden, basically like a phase type transition by which the oscillations occur. So collective oscillations and synchronization, the type of models that have been used in the past, really this is the huge framework, is the Kuramoto type models, where there's ODE coupling through networks or activity matrices or whatever, right? And typically synchronization here occurs, right, as the coupling strength increases, right, by measuring the Kuramoto order parameter, right? Other ways are more kind of based on kind of writing down in a kind of a little bit of an ad hoc way, right? Field equations, PDEs, reaction diffusion systems, right, that can give rise to target and spiral wave patterns of cyclic AMP and social amoeba, right? So this is useful, but kind of phenomenological. There's an interesting class of models that are PDE-ODE based, but where the diffusion is, there's no cells, but the diffusion is based on a discrete Laplacian restricted to lattice sites. And this gives rise to a huge computational effort for which you cannot really do too much analysis. But the framework that we're going to do today is really inspired by the group at Munich, Mueller and Kudler, Christiane Kudler, right, which is coupling individual cells through a bulk diffusion field. And these original papers were really the inspiration for the model I'm going to describe. Okay, so what's the model? So here's a cartoon here, right, of a two-dimensional cell, of a two-dimensional domain. The blue things here are supposed to be circular disks. Okay, inside each of the circular disks, you can have NODEs that are reacting by however you want to prescribe the reactions. So here I've got two of them. Okay, so only one of them can go across the cell membrane. The membrane is permeable to one of the species, comes out as a red dot, and then it can diffuse to its neighbors. Okay, so inside the cells, if they were uncoupled, you can have a large system of ODEs, whatever signaling pathways you think are reasonable. In the bulk region, the red dots diffuse by just a passive diffusion equation. But across the cell membrane, regulated by permeability parameters, there's a coupling between the bulk medium and the intracellular intracellular levels, and there's the red guys can go across the membrane and go into the bulk, regulated by an efflux parameter. So the scaling limit we're going to do so that we can do some analysis is where the size of the cells is sigma, right, divided by the length scale of the entire confining domain is much less than 1, right? And the permeability parameters I'm going to take to be large so that you see that there's a transport across this boundary. The boundary conditions on the entire domain are reflecting so that no chemical can leave the domain. So the parameters are going to be the bulk diffusivity, the bulk decay rate, KB, the permeabilities, the small aspect ratio, and then the time scale of intracellular reactions. So here's the mathematical model. In the region exterior, inside the domain, but exterior to the cells, you get passive bulk diffusion, nothing interesting, right? Nobody gets out of the confining domain. On the boundary of each cells, there's your permeability parameters. There's a Robin boundary condition that measures the exchange. Notice that I have UJ1. So only one chemical can be transported across the domain. For simplicity, we're going to take each disk has radius sigma. It's a circular disk centered at some point in the domain. I'm going to take disks of the same radius. The coupling then to what's going on inside the cell, right, is by an integration here, this term, over the cell membrane. So there's the integration over the boundary of the cell of the Robin boundary condition. E1 here is the unit vector only for the component that can go across the cell membrane. The rest of them are 0 because they're impermeable for the other chemicals, right? Kr is a reaction rate, and there's the intracellular dynamics, however you want to put, right? So the intracellular reaction rate here is Kr. So whatever you want to put here for the intracellular dynamics, whatever signaling pathway you think is reasonable, right? You go ahead and put it there. And this holds for each of the cells. So PDE coupled to an integral differential equation through an integration over the boundary. Okay, so in dimensionless form, you can cast this system into what I have here, bulk diffusion, Robin boundary condition on the boundary of small disks of radius epsilon, common radius epsilon, n interacting species, right, which I write here as a vector here of length n, with intracellular dynamics as follows, right? Coupling due to integration over the boundary, but only the first chemical, right? Only the first chemical. So the key bifurcation parameters in this model are the following. The permeabilities, right, which are these D1Js and D2Js. D1J is an influx, measures the influx of the chemical into the cells. D2J measures the efflux of the intracellular component out of the domain. There's the ratio tau of the reaction rate, right, of the intracellular reactions over the decay, basically the decay time scale of the bulk signal. If tau is very, very large, the bulk signal you can think of as hardly decays. It's almost pure diffusion in the outer bulk media. And then there's the normalized bulk diffusion coefficient, right, which is given by this. So here is the model that we want to look at in the limit epsilon going to 0. Okay, so here's the question. Can one trigger oscillations through a Hopf bifurcation that wouldn't otherwise be present without the coupling via bulk diffusion? So I'm going to consider an example for which each cell is a conditional oscillator. When uncoupled from the bulk, there's no oscillations. So you might think that what I need to get oscillations for the full coupled system is that the ratio of the chemical reaction inside to the bulk decay timescale, right, has to be in some interval. Bigger than 0, can't be tending to 0, it can't be infinite, it has to be in some time, it has to be in some interval. And from this model, can we exhibit what I said before, quorum sensing behavior determined by the cell density, diffusion sensing behavior, that oscillations are triggered by the diffusion coefficient and the cell configuration. And it turns out there's 3 key parameter regimes, distinguished limits for this bulk diffusivity. D is order 1 as epsilon goes to 0. The spatial distribution of cells is very key, right? I cannot think of this as being a well-mixed limit, right? Then this one here where D is much larger than minus log epsilon, this third one here, is the classic well-mixed regime, where essentially the PDE-ODE system reduces to a finite dimensional ODE system with global coupling. And it's this type of system that has been kind of ad hocly plunked down in the literature to examine quorum sensing behavior. But there's a regime in between here and here that we've identified. It's the regime for which D is order minus log epsilon. In this case, in this regime, we can calculate hop bifurcation thresholds by an easy approach. And you can also derive a reduced ODE system from this model, right? But where you still see the effect of the cell locations, right? And also the diffusivity. In the classic well-mixed regime, there's no effect of the cell locations, right? There's no effect of D, it's just the global coupling. So how do we do this? We use strong localized perturbation theory to construct steady states. We analyze the linear stability problem and then derive the reduced ODE dynamics and compare with full numerical simulations, right? So the steady state framework, right? I'm not gonna go through this too much because this is, asymptotics relies on kind of how do I put it? Not everybody has the background with matched asymptotics and so I'm not gonna go through this too much. But essentially the cells look like point sources in the limit epsilon going to 0. So it's not surprising that the bulk diffusion field at steady state is a sum of Green's functions, right, in that limit, right? And so what you can derive for the to calculate the steady state is a nonlinear algebraic system, which I've written here, right? A nonlinear matrix algebraic system for the strengths of the Diracs corresponding to the cells and the intracellular concentrations. And I'll have this better on the next slide. But the interaction for the steady state is mediated by a Green's matrix, this G, right, as I've written here, which involves the reduced wave Green's function for the domain. So the Green's matrix involves this Green's matrix. So you can calculate and you can reduce the steady state problem to a nonlinear algebraic system. And then you try to study the linear stability of the steady state. You introduce a perturbation as usual, okay? But what you end up getting, and the next slide will be much cleaner, what you end up getting, right, for the stability is that the discrete eigenvalues lambda, right, are obtained by a root finding condition on the determinant of an M by M matrix, where M is the number of cells. And this is in terms of a full Green's matrix that depends on the eigenvalue parameter. So here the Green's matrix is built up of tau, lambda, and D, right? So this will determine the eigenvalue, the linearization. And where the intracellular kinetics come in is through this diagonal matrix K, right? Which, because it's a rank 1 coupling, only involves the cofactor of the Jacobian matrix, the first cofactor of the Jacobian matrix. So it's given by this formula. So JJ, this guy here is the Jacobian of the intracellular kinetics at the steady state, right? What goes into here with this W, and so and this H are the permeability parameters. This is written better in the next slide. So this GCEP matrix is a symmetric matrix, but it's not Hermitian when I'm looking for a hop bifurcation, okay? But the result is for epsilon tending to 0, the discrete eigenvalues of the linearization of the PDE system around a steady state is in this set. It's a set, capital lambda, of all such small lambda for which the determinant of m is equal to 0. Okay, so I have to solve a big nonlinear matrix eigenvalue problem. Okay, but the proposition that you can prove, right, at least from this formulation that you derive, is that a steady state solution is linearly stable, i.e., right? So this is a steady state is linearly stable when the real part of lambda is less than 0, right? And if the nonlinear algebraic system, right, has a non-degenerate solution, which means you're not at a bifurcation point, okay? Right? So then lambda equals 0 is not a root of this determinant. So what that means is that the way that you can get an eigenvalue to cross from the stable left half plane to the unstable right half plane cannot be through a 0 eigenvalue crossing if you have a branch of solutions that does not have a bifurcation point, exactly as you would expect. So you would think then that instability could be lost, right, through a Hopf bifurcation, through crossing the imaginary axis. Okay, now the eigenvector of this GCEP matrix has information on its own. The eigenvector, right, determines here, what is this crazy looking formula? This determines the buildup of the bulk chemical just outside the cells. Okay. Moreover, this matrix, right, the jth component of this matrix determines the relative magnitude of the size of the intracellular oscillations near a bifurcation point, near onset. Okay. So numerics for the GCEP, right, involves solving a nonlinear matrix eigenvalue problem of this form. As I've said, an unstable mode is a root of the determinant equals 0 in the right half plane. And the number n of such unstable modes is, of course, the number of such roots. Okay. So in open regions of a parameter plane, the tau d parameter plane, I want to know how many unstable modes do I have? So you can use a winding number computation, right? Implement that numerically to get a stability map. And then you can compute the Hopf bifurcation values by path following in D, but there's, as I'll show you, there's branch points and saddle node points, and so you have to use pseudo arc length continuation. Okay, so nonlinear matrix eigenvalue problems, right? There is a literature of people in numerical analysis that are working on implementing or devising good schemes for this, because they're typically not well conditioned to work with a determinant as its own, but they're usually restricted to a Hermitian case, or when m is polynomial in lambda or rational in lambda, or where the eigenvalue enters as a low rank perturbation. This is not what we have here, okay? But there are cases where you can make good analytical progress. So that's a concentric ring pattern of cells, right? Where you get a cyclic matrix for which you can identify the eigenvalues and matrix spectrum of the matrix M, right? You can have a defective cell at the center that triggers oscillations, which has an M-1 dimensional cyclic subblock. In the D is large regime, right? You can actually analyze that matrix M to show that there's only one of its eigenvalues can cross through 0. And so you can use a root finding on that explicit eigenvalue. And the reason why we use the unit disk is that we can have an explicit formula for the Green's matrices by using essentially separation of variables to find the Green's function in terms of k zeros and I zeros of complex argument. So we can get our handle on those. So the things I'm going to do today are connected where I'm going to choose one specific conditional oscillator for the intracellular kinetics, and it's going to be the Sel'kov model. 2-component intracellular dynamics, which is used for qualitatively modeling glycolysis oscillations. Okay, so forget about this, but it's 2-component model, right? For an isolated cell, you can find the steady state and you can find the determinant, right? And so in terms of these parameters, alpha j and mu j, for a single isolated cell, if you're in this green region, right, a single isolated cell is unstable to a Hopf bifurcation. There's a limit cycle oscillation and a periodic solution. So what I want to be is I want to be just above this curve. I want to be basically here, right? Or maybe just on here. I want to be just a little bit stable, right? So I'm stable, but due to the coupling with the cells, right, I can trigger an oscillation. Nature works in many ways where you're near a marginal stability threshold. So I want to be a little bit unstable, sorry, a little bit stable, but then have an instability triggered by the coupling. The advantage of the Sel'kov model is that the nonlinear algebraic system always has a unique steady state. So there's no zero eigenvalue crossings by the result we have. So instability is only going to be lost through a Hopf bifurcation. You can show that. Okay, so here's a simple analytically tractable example where you get a ring pattern, right? What's a ring pattern? You put here two cells, right, concentrically spaced on the unit disk. In the unit disk on a ring of radius R0. So the red thing there are the small cells, right? If you assume identical kinetics and identical permeability parameters, because you get a cyclic matrix, you can find the eigenvalues and spectra of this thing easily, right? And from this, you end up, the GCEP problem, which looks kind of complicated, becomes just solving a nonlinear transcendental equation for each mode, for the mode, basically the modes of a cyclic symmetric matrix, okay? Which is easy to do, right? So you want to compute then Hopf bifurcation boundaries in the tau versus D plane for each j equals 1 to m by setting lambda equals lambda I, right? Fixing the ring radius, whatever, doing continuation in D. Use your winding number to be able to determine the number of unstable modes in the right half plane. And as I mentioned, this eigenvector you get for free because it's a cyclic symmetric matrix for the Green's matrix. In particular, if m equals 5, right, you can show because of the matrix is cyclic symmetric, there's mode degeneracy. The asynchronous modes that are orthogonal to 1, 1, 1 have to come in pairs. So there's exactly two asynchronous modes, but there's the synchronous mode where all the intracellular oscillations will be the same. So qualitative questions. What's the effect of cell clustering? Smaller ring radius. What about changing the permeabilities? What about the number of cells? What about changing a parameter in the intracellular kinetics? Okay, what's the effect on that? So here's a picture from the computation that we have. Here's a phase diagram, tau versus D. These things here are Hopf bifurcation boundaries. This is the asynchronous mode, which means that the two cells will oscillate out of phase, predicted by the linear stability theory. Here's the stability boundary, Hopf bifurcation boundary, for the synchronous in-phase mode, right? So what do you see? And so the gray region, by pixelating the tau D parameter plane into a number of sufficiently fine resolution, although these things are discrete dots, it looks like a gray solid mass, but there's n equals 2 unstable eigenvalues in the right half plane for the GCEP in here. And when you cross in here, there's n equals 4. So this is for two cells. R0 is 0.75. So when you're inside here, I predict that you're going to get, for this value of D, right, you're going to be unstable to a synchronous oscillation. Whereas if you're inside of here, both the asynchronous and synchronous modes are unstable. If you just change the R0, the ring radius, what you end up doing is you move these boundaries a little bit. But here's what you get with full numerics: 0.1, 0.2, 0.3. 0.1, no oscillation, you're outside the lobe. The oscillation basically goes to the steady state. 0.2, right on the Hopf bifurcation boundary, right? Actually, these should be interchanged. This should be 0.3, this should be 0.2. This point here is right on the Hopf bifurcation boundary, which corresponds to this picture, a small scale oscillation, which suggests that the bifurcation is supercritical. Okay, 0.3, when you're well inside here, actually corresponds to this picture, large scale oscillation. Okay, then you vary the ring radius, right? What is the effect of varying the ring radius, right, on which the cells are located? So the shading of the different curves corresponds to 3 different ring radii. R0 is 0.25, 0.5, or 0.75. So 0.5 is here, 0.25 is here, 0.75 is here, right? Those are the synchronous lobes. And these little guys here near the origin in the tau D plane are the asynchronous lobes. So as you would expect, the asynchronous lobe, this dotted one here, is smallest when R0 is 0.25. Why is that? When 2 cells are pretty close together, they can really synchronize their activities pretty well. And asynchronous instability should only occur for small values of D, as you would expect. But R0 is 0.75, right? R0 is 0.75. The cell over here is close to its image on the other side of the domain through the Neumann boundary condition. Okay, so you have to be aware of that. But diffusion sensing, what is diffusion sensing behavior? Imagine D is 5 and tau is 0.6. D is 5, tau is 0.6. I'm right in here. Okay, so I'm outside the instability lobe for R0 is 0.5, but within the lobes for R0 equals 0.25 and 0.75. So a more clustered configuration will trigger oscillations. Why is R0 0.75 clustered? Because it has its friend on the other side of the boundary. Okay, so there's spatial cues coming in. Okay, so M is 5, you get a new phenomena. You put 5 cells on a ring, and here's what you see. I've just plotted the synchronous boundary. This region is open in the tau D plane. So when D is very large, you still see oscillations. You'll see oscillations. There's a window of tau for which you'll get synchronous oscillations. This picture here is a zoom of what's going on near the origin, where you see all the asynchronous lobes. You should see 2 asynchronous lobes because of the mode degeneracy. And here's my winding number calculation done honestly. Right? There should be no blue region because you're jumping from n equals 2 to n equals 6 to n equals 10, right? And the number of unstable modes here, when you're right near a Hopf bifurcation boundary, it's very hard to do a winding number when the eigenvalues are sitting right on the imaginary axis or very close to the imaginary axis. So it does it wrong, right? Unless I jack up the resolution, okay? But here, by increasing the M, the number of cells, you can get an oscillation in the Will mix limit on some intermediate range of the tau. Okay, what's the effect of a center cell that's defective? So this is another example that you can do a very nice theory for that's analytical on the GCEP matrix, where the ring cells are all identical. M equals 5 cells, 4 identical, 1 guy defective. Okay. So ring cells are all identical with these permeability parameters. And now here's a defective cell at the center with a small d1. What does d1 mean again? d1 is the measure, the influx of the bulk signal into the cell. So this guy here is not as happy to absorb the bulk signal into this cell. So what do you see? All cells identical, no defective cell. The region is unbounded in the tau D plane. However, when this guy here is not as happy to absorb chemical from the bulk medium, right? The lobe is bounded. The lobe becomes bounded, right? So it's harder to trigger intracellular oscillations for large D. They don't exist. And here is a zoom of what is happening near the origin for this picture showing the asynchronous lobes. But it's exactly what you would think, and you can get a nice root finding condition for this. Right? Maybe I won't do this one, but you can say something also about what happens when you change the intracellular kinetic parameter, right? So the defective cell now is closer to going unstable when isolated. It's just a little bit above, right? Here is what happens for 2 values of the ring radii when they're identical cells. And here is what happens when the center cell is closer to going unstable when isolated. As you would expect, right? It's easier to trigger oscillations in the case where the center cell is defective. So what do you see? The instability lobe here exists up to here. Here it exists only up to 2.5. And so small changes of the intracellular kinetics can have a large effect in this region. With more cell clustering, right, you can have a larger bulk diffusivity, right, before the bulk chemical is washed out. But small changes in a defective cell, right, can influence the synchronization drastically. Okay, let's come to this. D is large. The D is D0 over nu limit. That awful GCEP matrix for which I have to use a root finding, and I take an arbitrary arrangement of cells. No cyclic pattern, no cyclic, no ring pattern, no ring center cell, arbitrary location. But I'm going to use this regime to simplify something. So in this case, the Green's matrix, right, you can approximate, right, to be essentially a multiple of an identity plus the Neumann-Green's matrix. From this, there's a calculation you can do that shows that only one eigenvalue of the GCEP matrix can cross through 0, one eigenvalue sigma. The rest of them are bounded away from 0. So there's only one root finding condition to be able to isolate the effect of oscillations, right? So this is a great simplification and ends up being that a discrete eigenvalue, the linearization lambda star, is a root of this problem, right, QS, which involves the locations of the cells, right? The V1 here is 1 over B1, and there's the intracellular kinetics, depending on lambda. These are the permeabilities, but it's basically a scalar root finding problem of some complexity, but it's scalar after all, right? The hot bifurcation boundaries are obtained by setting the real part equals 0 and the imaginary part equals 0 when you set lambda equals I lambda I, which is a really good simplification. Right? In this regime, right, you can also derive an ODE system that we'll use in our comparisons. When D is D0 over nu, we have worked out recently a PDE-ODE system reduces to an ODE differential algebraic system for the average of the bulk chemical, right, and the intracellular concentrations. So here, and this B here is determined by the Green's matrix. So there's the Neumann-Green's matrix, which involves the locations of the cells. It involves the permeabilities in P1 and P2. It involves nu, which is -1 over log epsilon, but it still sees the diffusion coefficient. It still sees the effect of the locations of the cells. And it's not the classic ODE system that people would ad hocly write down for the well-mixed regime. Okay, so let's do some examples of something of higher complexity here, right? I take my baseline parameter set and I'm going to vary the influx permeability rate, D1, into the cells. That's how well each cell is able to absorb the bulk, how willing it is to absorb the bulk chemical that comes from all the other cells. Here is the hot bifurcation boundaries in the tau versus D0 plane for a pattern of cells that looks like this, 2 clusters of 5 cells, right? And there's located like this. So then this figure, there's 3 different curves. One, the dash curve, this guy, is where you have identical cells. The thin solid curve, which is this guy, which doesn't exist for large D, is where D1 is equal to 0.8 for this group and D1 is equal to 0.4 for the second group. The heavy solid curve, this guy with a now sharp nose, is where you have non-identical cells with D1 uniformly distributed on 0.4 to 0.8 for all these cells. So what do you see? If all the cells are identical, they synchronize their behavior really well for large values of D. If you fix a value of D1 specifically for each of the 2 clusters, oh, they don't oscillate except in this little region, right? Random is somewhere in between. Now, what are these dots here? That's where I'm going to show you here the full numerical simulations. But the hot bifurcation boundaries depend sensitively on D1. That's a key point. The permeability, it depends sensitively on this. So the red dot, we should see with identical cells intracellular, we should see intracellular oscillations that are synchronized. Here's the plot of the full PDE solution at time t equals 400. Here's the average bulk, there's the bulk concentration at, I think it's this point up here versus time. This comes from the full flex PDE simulations. This is from the ODE system that I've written down on the other slide. Notice here, right? What you see is the black guys, oh, ODE system agrees very well in terms of amplitude and the period, right? The blue guys agree very well in terms of amplitude and period. So the ODEs here work very well, and you get nearly synchronized intracellular oscillations. I only showed you the chemical concentration in one cell. Okay, now you go to the blue dot. Where's the blue dot? I'm right in here. D is kind of small. What do you see at the blue dot? Okay, so this is the case where I have D1 is 0.4 and 0.8 in the two clusters, right? So here is from there's the full flex PD simulation. You see really a buildup of the bulk chemical. There's usually see diffusion gradients, right? Here is from the ODEs that you would expect. There's a small phase shift between the oscillations, but as you would expect, D is small. The ODEs don't agree so well, right? As you would expect, they don't agree as well as in the previous case, right? But generally, it gives qualitatively the right thing, but you're using it in a regime for which you shouldn't do it. Now, what happens over here at these dots? Red star, blue star. There you see the steady state is stable. At the red star, right, you see an oscillatory. This is the flex PD simulation, the first row. This is from the ODEs, just with different initial conditions, but the steady state value is the same as predicted by flex PD and the ODEs. Monotonic approach to the steady state, oscillatory approach to the steady state, and that's because the eigenvalue in this case is slightly in the left half plane, right? So it's like a decaying oscillation, a decaying damped oscillation. Okay. Now, here's a picture that I like. I'm coming close to the end here. This is a complicated picture, so it'll take a minute to explain this, right? I want to explain pattern of two rings and two isolated cells. Two isolated cells by their own. I'm going to fix tau and vary D, and I'm going to use that baseline parameter set. That was two permeability parameter sets, capital 1 and capital 2. For capital 1, D1 is 0.8 for the ring cells. So they all have a relatively large influx. D1 is 0.3 for the isolated cells, okay, where it's reversed for pattern 2. Okay, this picture here for the left pattern, the left thing, it pertains to pattern 1. The right one corresponds to pattern 2, and it's a figure with two y-axes. I want to show you the information that's encoded in the eigenvector of the GCEP matrix. So for this case 1 here, there is no hot bifurcation boundary in the tau D0 plane. The large D theory that I give you gives you no oscillations. What do you see here from computing directly the root finding on a 10 by 10 matrix, determinant M equals 0, right? Is you see that so I plotted here the dominant eigenvalues. You see the zero crossing occurs for D, not Z0, this is D, basically like 0.15. There's two different modes here that can be unstable. So let's look at these two, right, where I've got my cursor. In phase cells, so where the cells are in phase, right? And then you get an anti-phase, right, for the isolated cells. Right, that can be unstable. So if D1 is 0.3 for the isolated cells, these guys communicate really weakly with their neighbor on the other side, right? So what that means is that you should be unstable to a mode that looks like this with all the other cells being quiet. So what am I plotting here on the right axis? This is a measure of the strength of the intracellular oscillations within within the isolated cells. C1 corresponds to this cell, C2 corresponds to that cell, and it's normalized to be 1. So if this guy here is near 1, it means those two guys are oscillating strongly, these guys are quiet. So what do you see? Exactly as you would expect, right? Right? That if D1 is small, these guys here exhibit very strong anti-phase oscillations, right? And also the in-phase mode also has a very strong C1 and C2, with the other ones being quiet. Look how this differs here if you just change these permeability parameters, right? What you see is the two unstable modes are the in phase, where they're all in phase, but where the two cells have an anti-phase component, these guys being quiet. In other words, this dotted line here is always stable when you change the permeabilities. So let's do a numerical computation right at this point. D is 0.05. What should you see? You should see in the two cells, two isolated cells, you should see a superposition of an in-phase and an anti-phase mode. You should see in the other cells, cells 3 and 4, 7 and 8 in here, essentially no oscillations at all, right? Because the diffusion coefficient is too small, they're hardly oscillating. So the linearized theory here predicts things really well, right? I know this is a full numerical computation in the nonlinear regime, but the linearized theory has a lot of information. Okay, I don't have time to do this, the D large regime, right? I'm gonna do this, but here's my further direction, which I would love to know how to do. Give me 100 cells, arbitrarily placed in the domain, no symmetry, no anything, right? Not D large. Can you extend these numerical analysis tricks to find numerical algorithms for root finding, right, on problems of this type, right? Sel'kov is a toy model. No biologist would believe this in a million years. What happened? But the framework applies more generally. If you want 5 ODEs, you have a realistic model of glycolysis, which exists out there. Put it into this framework. Actually try to match with numbers. What about things other than a disk? Okay, we have to find the Green's matrix by some type of spectrum, by some type of fast multipole methods. Transitions due to jumps between stable, steady states, no oscillations. What about two bulk diffusing autoinducer species? Turing instabilities with equal bulk diffusivities. Can you get membrane permeabilities to give rise to a Turing bifurcation with equal bulk diffusivities? What about 3D? Okay, where interactions are much weaker. And so here are the paper that we took, Mueller's model, and here's something that has, I did not talk about this one today, but it's the well-mixed limit of just ODEs, where we have 1,000 cells. But what I focused on today was this paper here that we just submitted to SIADS, which really has to do with diffusion sensing. Okay, I'll stop here.